So today we're going to be looking at the 6.7 material. It's working with integer exponents and the scientific notation. So we're going to try and split these up into two subparts of this overall section and look at them individually before we bring them all together. So the first part that we have is working with the integer exponents. The main ones that we're focusing in on are negative exponents, and then quotients that are being raised to powers that have negative exponents associated with them as well. So I'm going to highlight the specific bullet points within this that I would recommend that you write down for yourself. And I'll give a little bit of a pause before we actually start talking about these. So our main ones we want are first property here, warning that we have here, which I would highly recommend. You put some stars around it. And this last bullet point here, because this also corresponds with the one directly above it. In terms of the quotient to a negative exponent property, we're going to want both of these written down as well. Alright, so I'd take a moment, as much as you need to pause and write these bullet points down in your notebook for yourself as necessary. We'll talk about them here shortly. So getting into negative exponents. A negative exponent shows up specifically when we are working with adding or subtracting exponents together, and then we somehow get a negative result showing up out of that. The big thing that a lot of people get mixed up with the negative exponents is that they assume that the negative that's going along with that up here is somehow going to affect the base value down below here, this a value. And while it does actually affect its placement in a fraction, it does absolutely nothing to change the sign of the base itself. So this goes back to when we're beginning to talk about exponents. It's very, very important to correctly identify what is the base value that is being raised to an exponent. Is it a 5? Is it a negative 5? Is it a positive x or is it a negative x? Is it a positive 15.3 or is it a negative 15.3? All of that's very useful information to have, but when we're working with negative exponents, we do not really care about the sign of the base. Again, if we're looking at it, this a value right here, we do not care if that is positive or if that is negative. The negative exponent does absolutely nothing to affect that value. It's the number that's associated with the exponent that will change things. So the negative only is going to change where our base is in a fraction. And we see the two scenarios playing out right here. If our base, which is a in this point, is in the numerator of a fraction at the beginning of the problem, then this negative exponent is going to move that base to the denominator of the fraction. And after that, we can drop the negative in the exponent spot, and we're just left with an n left over. That's all that can be left from there. We would deal with that exponent accordingly, if possible and if necessary, based on the problem and the numbers we've been given. Our other alternative is we've been given 1 over a to the negative n power. And kind of conversely to what we did with our first example we did there, we have the base currently in the denominator of a fraction. So what is this negative sign in the exponent going to do? Well, it's going to move this base from being in the denominator of a fraction into the numerator of a fraction, like we have right here. And we get a to the positive n power. So all that the negative sign does, the exponent spot, it moves the base to its opposite location in the fraction. That is it. It doesn't change the sign, doesn't change anything else about its value, it just flips where it is in the fraction. That's all that we have showing up with that. If we take a look at the quotient to a negative exponent property rule, this is actually the larger, more all-encompassing version of the negative exponent, but we see it demonstrated more specifically with an actual fraction in this regard. So looking at our example that we have here, we're assuming a and b are numbers. They can be positives, they can be negatives, they can be fractions, decimals. There's not going to be 0. It's the only exception we have with that, because we can't divide by 0. So if we're starting off with the fraction a divided by b, and that whole fraction is being raised to the negative n power, then if I'm going to apply that negative in the exponent spot, all that's going to do is just flip the fraction. The numerator a becomes the denominator a. The denominator b now becomes the numerator b. So the fraction just flipped upside down, essentially have the reciprocal of it, and the negative sign goes away in this exponent. Now, if a or b were positive or negative, that doesn't matter. It's completely irrelevant. The negative exponent doesn't care about that. It doesn't care about the sign of the base. It just cares about flipping it. It's the only thing that it does, and the only thing it's going to do with these problems. So when you are working with integers being raised to exponent values, specifically negative exponent values, take a minute and pause to realize that the negative exponent isn't going to change the sign of the base. It does not change that in any way, shape, and form. So we deal with the negative sign in the exponent spot all by itself, then we deal with the number right after that. So we're going to go through a couple of the examples that we have right down here and see this in full effect. So looking at our first example, we have 3 to the negative second power. So when we're looking at these, I generally tend to gravitate towards wanting to take care of that negative sign first. That does the really weird stuff with these types of problems, so I like to take care of that before I deal with the 2 that's up in that exponent spot. So as we talked about previously, the only thing that the negative sign is going to do in the exponent spot is flip where the base of this exponent is going to be. So currently, 3 is sitting in the numerator spot of a fraction. If you need to, you can write in the invisible 1 that's sitting down below there for yourself, but it's not necessary. So if the 3 is in the numerator spot, it's going to need to be rewritten into the denominator spot. The numerator is therefore then replaced with a 1, and the denominator becomes 3 to the second power. From here, now the negative in that exponent spot is gone, which is great, and now we can just apply that exponent of 2. So 3 squared, it's going to give me 9, and I get 1 over 9 as my final answer. Let's take a look at a second example that we have here. Take a look at number 2. Oops, over a bit. And here we have 1 over 4 to the negative third power. Once again, for me personally, I'm not a fan of negatives. I think they're a little bit weird to work with. And how do we start off with taking a negative third power? Well, let's deal with that. So in this instance, we have 4 as the base of the exponent. That base is currently in the denominator of a fraction. So to get rid of that negative in the exponent spot, I'm going to take the base of 4, and I'm going to move that into the numerator of a fraction. So we end up getting 4 to the third power. And now from here, 4 to the third power, we can apply a calculator if necessary to find out what that value is. And 4 to the third power is going to equal 64. Get to our final answer there. When we get to actually number crunching these things, if you have some number raised to a larger power, go ahead and use a calculator for it. That's perfectly fine to number crunch the final answer there. Let's take a look at number 3. So here, we now have a negative base being raised to a negative power. You might be thinking, okay, well, I've got a negative and a negative, that makes a positive, right? Well, again, if we are just going to take care of the negative exponent, then that's fine. Let's do that first. So remember, the negative exponent does not care about the sign of the base. All it's going to do is just flip the fraction. So applying that negative in the exponent spot, I don't care about the sign of the base, I just care about flipping the base. Make this a better 6, maybe. There it goes. And now I get the quantity of negative n over 6m, all raised to the second power. Now I can apply the exponent of 2. If need be, you can expand this out for yourself. Don't have to, but this is an optional in-between step. And it is only at this point in time, because we've expanded this thing out and we see that now we have a negative times a negative showing up, now we can determine, oh, we're going to have a positive fraction for our final answer here. Multiplying fractions, we go straight across. N times n is n squared. In the denominator spot, we have 6m times 6m. It's going to give me 36m squared. Final answer there. In our fourth example, we have negative of 1 over 7 to the negative second power. So again, here we need to identify what is the base, what is the exponent. So in this case, the base is just going to be this 1/7. It's everything in the parentheses that's being raised to the negative second power. This negative out front is not inside the set of parentheses, so we will not include it with this exponent and all the things that are going to go along with that. So this negative sign, all what that's going to do is it's going to flip the fraction inside here. The negative sign out front stays the same, and we just flip this fraction inside. It becomes 7 over 1. A little bit of a rewrite here. Let's make this a little bit nicer for ourselves. Let's just make that 7. So now I have the negative 7 raised to the second power. Well, 7 to the second power, that's going to be 49. Again, the negative out front is not being affected by that. And we just get negative 49 as our final answer. So as we see with all 4 of our examples here, we need to correctly identify what is the base and what exponent power is it being raised to. Remember also that the negative in the exponent spot does not automatically change the base to become a positive or a negative value. The negative exponent just flips the fraction, or just changes where in the fraction our base is. That's all it does, nothing else. So bringing things back to our notes, what we have over here is just moving a little bit farther down the notes we have. With these properties with negative exponents, this means that no polynomial final answer that we have may contain negative exponents. It's a really fancy way of saying all of our answers need to only have positive exponents moving forward from here. So this goes on all of the homework, on all of the tests, on all the exams you might be given, everything with positive exponents. There's going to be one exception to that we are going to see with the scientific notation showing up later on. But again, that is the lone exception to this. Everything else, when we're working with just fractions and polynomials, that is all going to be, you're going to be required to have only positive exponents for your final answers there. Now, with this, I want to present this to you guys as well. Here's all of our exponent properties. It's a summary of all of them. If you do not have these written down for yourself, I would write all of this down. I would pause the video and take a moment to write all of these down for yourselves. You are going to need all of these moving forward in this class and your future classes, because these are all the exponent properties that you could be seeing. So I recommend pausing the video here for a couple seconds, or a minute or two, however long you need, to write these down for yourself. And then we'll continue on looking at these examples. With the examples that we have listed here. We're going to take a look at these 4. We'll go through those as if we were given them on the homework or on the test. All right, so our first example has us working with x to the negative 4th power times x to the 13th power. Now when you're approaching this, you have several options on what you could do to simplify this thing down. You might be looking at this going, well, I have 2 bases that are the same and multiplying together. I could use the product rule to simplify these exponents down, and you absolutely could do that. You could be keen in on saying, well, I have a negative exponent showing up. I want to rewrite that negative exponent and get rid of it, and then I'll deal with whatever comes afterward. You could do that too. There are several options with pretty much all of these problems, so there's a lot of routes you can take. At the end of the day, I feel like your best route is to pick one that you are most comfortable with doing and then commit to that. So I'm going to show number 1 here with 2 routes that you can take to get to the answer. I'm not going to show that with the other problems only because of time, but with a lot of these you do have multiple routes and numerous methods and things at your disposal to get to the actual final answer with these. So for this first one here, let's go with this first option that we had here. We notice this is we have 2 bases multiplying together. So this is an application of the product rule. Product rule states that if the bases are the same, which they both are, they're both x, and they are multiplying together, which they are, then the exponents are going to add together. So we get x to the negative 4 plus 13 power. Now negative 4 plus 13, that's going to give us 9. So this thing becomes x to the 9th power. And there we have our final answer there. This is one route you could take. Alternatively, if you're looking at this going, I want a different route, I don't want those negative signs in there, in the exponent spot, I want to deal with that first. Okay, then we can apply the negative exponent property, which says I need to take the base and rewrite that thing. Now remember, the negative exponent, as we saw with the previous examples, just changes the base from where it is in the fraction to its opposite spot. So currently the x, this front term here, or this front value here I should say, currently it's in the numerator spot of a fraction. The negative sign is going to flip that and put that in the denominator spot of a fraction. So this thing becomes 1 over x to the 4th power. And it's still being multiplied by x over, or x to the 13th power. Now if I multiply these two things together, multiplying fractions, we go straight across. We get x to the 13th power over x to the 4th power, and now we have the quotient rule showing up. Quotient rule states that if the bases are the same, and dividing, then the exponents will subtract. So we get x to the 13 minus 4 power, all inside parentheses, and then 13 minus 4, that's going to give me 9. So as we're seeing here, gain the same answer either way. So when you are approaching these problems, I'm hard-pressed to say that there is a clear and obvious better choice, better selection to make between these two decisions, these two routes that we have here. We're going to see in a couple other examples that there are a few other routes that you could be taking. You might notice other routes that you could be taking. Yeah, choose one route, choose one property at a time that works for you, and then just start working this thing out and seeing how it unravels. Let's take a look at a couple other examples with this. So again, drawing from the same examples that were listed on the notes. We're now looking at 2b to the 3rd. Oops, that's inside of parentheses. All raised to the negative 4th power. Now again, for me, I'm looking at this going, okay, I can't do anything inside the set of parentheses, but I have this negative sitting out front, and I want to deal with that negative first. So all the negative does is it says take whatever the base is and flip where it is in the fraction. And then we can drop the negative in the exponent spot. So we get 1 over 2b to the third power, all raised to the fourth power there. And now I can apply my knowledge of raising things to the fourth power. I'm going to get 2 to the fourth power, which is going to give me 16. I have b to the third raised to the fourth power. So let's do a quick rewrite. Maybe we're a little unsure about the power rule here. That's fine. But now I have the power rule showing up. I have an exponent raised to a power. That means that these two things are going to multiply together, and that's going to give me b to the 12th power. I have no negative exponent showing up, so there we go. Got my final answer here. And we're good to go. Looking at our third example, we have x to the 7th over x to the negative third power. Again, we're looking at this. We have two options. We can either work with the negative exponent, or we can work with and see what happens from there. Or we can notice, hey, the bases are the same and they are dividing, so I can apply the quotient property. Either route you would like to take is your choice, your call. They can get you the same answer. Just make sure you're being very precise in the steps that you are taking to get there. So I'm going to use the quotient rule. The bases are the same, and they are dividing, which means the exponents are going to subtract from one another. The numerator minus the denominator. So in this instance, that gives me x to the 7 minus negative 3 power. I'm going to do a rewrite with that because I don't like double negatives, or double signs, I should say. So this becomes x to the 7 plus third power. And this then becomes x to the 10th power. We have our final answer there. Again, with a lot of these, several routes you could take to get to the final answer. It's very much one where you need to make a call on which one you would like to use or which method you would like to use and deal with it accordingly. If we're unsure about using those properties, my recommendation is, again, review those, have those sitting next to you as you're going through these problems, and then just apply them one at a time as you're going through this. So for number 4, I'm looking at it's going, okay, I've got a whole bunch of things multiplying together. I have this first set of stuff multiplying together. I got the second set of stuff multiplying together. I've got some negative exponents in this one. I've got some negative exponents in this one. So I'm going to do a rewrite of each of these things. And I'm going to make this so I have no negative exponents here, no negative exponents here. And we'll see what comes out of that. Maybe that'll make things a little bit nicer. So doing that rewrite, I'm not actually doing any computations with these things. We're just rewriting each of these. So in the first one, we had x raised to the negative 5th power, which means the 3 and the y are going to stay where they are. We get 3 times y to the 7th over x to the 5th. And for my second one, the negative sign is going to stay. The x to the 4th is going to stay. Y to the negative 2nd power, that negative exponent is just going to move that y to the denominator spot. So now I have this thing rewritten. Okay, I have no negative exponents anymore, which is nice. Step in the right direction there. So let's go ahead and let's multiply these fractions together. I multiply fractions straight across. So in the numerator, I have 3 times negative 4. That's going to give me negative 12. I have y to the 7th times x to the 4th. Can't really do anything with those, but I am going to write them in alphabetical order. That's a bit nicer to see. In the denominator spot, I have x to the 5th times y to the 2nd. Again, different variables, or different bases, I should say. So I can't do anything with that. I'm just going to stay written like this. And now I'm noticing, well, okay, now I have an x variable in the numerator and the denominator spot. I also have a y variable in the numerator and the denominator spot. So I can deal with those individually. So if I'm dealing with the x's here, that's the quotient rule. is going to have negative 12 times x to the 4 minus 5 power. For the y's, doing the same thing, quotient rule. Y to the 7 minus second power. Make it negative 12 x to the negative 1 times y to the 5th power. Okay, now I don't have any duplicates of variables showing up. That's good. I have one negative exponent. I need to deal with that before I get to my final answer. So I have negative 12 y to the 5th. That negative in the exponent spot moves the base from the numerator to the denominator, and therefore get this thing simplified down to negative 12y to the 5th all over x. And there we'd have our final answer. So as you are looking at these 4 examples that we did here, again, we have numerous options and numerous routes at our disposal to get to each of these final answers here. But at the end of the day, it's your call on which route you would or wouldn't like to take to simplify these things down. End of the day, pick a property that stands out to you that you know beyond a shadow of a doubt you can apply, and then just try it. See what happens. Okay, what's the new thing that you get? Try that, see what happens, and go through it there. So this is the first part of 6.7. It's working with integer exponents and all of those properties. The second half of 6.7 has us working with scientific notation. And the main uses of scientific notation are ways to rewrite and express extraordinarily large or extraordinarily small numbers in a it's intended to be a cleaner way than the big long numbers and number of digits that we have shown up here. So if you have something that is 10, 20, 30 some odd digits written out, 1, 2, 3, 4, 5, 6, 7, 8, 9, then repeating that over and over and over again, well, that can be really painful, and we don't really want to do that if we can avoid it. So we are going to use scientific notation to condense some big number down into a smaller, more manageable set of kind of expression and notation. The same thing goes if we are working with an extraordinarily small numbers, like 0.00000, we go out a whole bunch of different places, 173. And instead of writing out all of those zeros that might be showing up in front of that thing, we can instead use scientific notation to write that in a shorthand method. So we have our two ways of rewriting these things. So we have our two notations. We have decimal notation showing up with both of them. Decimal notation is our standard way of writing numbers out. So you're writing the full-blown number with all the decimal places or with all of the digits and commas that are showing up in that thing. Scientific notation is the new one that we have, and it's the shorthand version of it, of those big numbers or those really small numbers. So here's the form that we have written out here. Scientific notation is of the form a times 10 to the n power. A is assumed to be some number. It can be anything between 1 and 10. It cannot actually be 10, though. So anything smaller than 10, like 9.9999, going out a bunch of different places, that's fine. And anything bigger than or equal to 1. So this is our range of A values in here. So this is a pretty strict rule with scientific notation. So we can only have something out front here that has one digit in the ones place for thinking of writing it as a decimal. And then the times 10 to the n power, that n that we have up here for the exponent, that has to be an integer value. It's a 7, a 13, a 5, a 100, whatever it may be. But it has to be an integer value. This does also mean that because it's an integer value, it could also be negative. We generally see the negative show up when we have more small numbers in our final answers. Big, huge, terribly small, or not huge, I guess they're small. Very, very small decimal numbers showing up. But suffice it to say, our n value could be a positive, or it could be a negative. It all depends on what original thing is we've been given to start with. So our first process that we have here, and I would recommend if you need to, take a moment to pause the video and write this down for yourself before we go through this. So our first step tells us that we are going to move the decimal point so that the first factor is greater than or equal to 1, but less than 10. This is going to make sure that we are meeting this A requirement here. A needing to be greater than or equal to 1 and less than 10. So in counting this thing over and moving the decimal place, we're going to literally be counting over how many places we have with this. So we're going to see an example of this method here shortly. While we're moving that decimal place over, in step 1, we want to be counting the number of decimal places, n, that the decimal point was moved. So we're counting over 5, or we're counting over 7, or we're counting over 13, whatever it may be. Will vary based on the original number that we've been given, if it's a big number or if it's a small number there. Now this is the part that generally gets a little bit confusing for people and trying to make sure whether we're going to have a positive or a negative integer for our exponent showing up. So what we're going to do is we're going to write down the number as a product with a power of 10. What this means is, was our original number greater than 1? And if so, then that means that that n value that we have is going to be 10 to the positive n power. If the original number that we were given was between 0 and 1, meaning it was a really big decimal that showed up, then the power is going to be 10 to the negative n power. So we always have to determine, am I starting with a very big number or am I starting with a very, very small number? If it's a big number, we're going to have a positive n in the exponent spot. If we're starting with a very, very small number, then we're going to be having a negative n in this exponent spot. And we can check our answer by plugging things into the calculator if necessary. Let's see if we get our original number that we were working with. So at the end of the day, it's going to be, what are we starting with? Moving the decimal left or right and counting how many places we're moving it to. Rewriting it so we have that original number out front times 10 to the, is it going to be a positive or a negative integer coming after that? And then we're done. So we'll take a look at these two examples that we have right down here before we go into doing the reverse of writing these things out in a different way. Working with our first number here, 48,300, we are going to convert that into scientific notation. So my first recommendation for everyone here is that we need to rewrite the original problem with the decimal place actually written in. This is going to help us with our first two steps as we're moving these things, this decimal point around back and forth to get to our new number. So step 1 says to move the decimal point so that the first factor is greater than or equal to 1 but less than 10. So we're going to do that by going and moving this thing over accordingly. So our new number, when it's rewritten, 4.83. Okay? Now our second step said to count the number of decimal places, n, that the decimal point was moved. In this case, how many places do you move this thing? We moved it 1, 2, 3, 4. So we have an n value of 4 here. Now, question becomes, we need to write down, for step 3, write down the number as a product with a power of 10. So, is this going to be 10 to the 4th power or 10 to the negative 4th power? We can think of it like this. Was our original number bigger than 1? And if so, which in this case it very much was, then we are going to have a positive 4 in our exponent spot. And therefore our final answer is going to be this 4.83 times 10 to the 4th power. And there we go. We've just converted 48,300 into scientific notation. Let's take a look at our second number that we have here. So we're working with 0.001. 0.0129. And again, I think it's always useful to do a rewrite somewhere on your paper when you're going through and modifying this thing. Okay, so our process says to move the decimal point. So the first factor is greater than or equal to 1, but less than 10. So I found my decimal place. I'm going to move it over to here, which means this thing gets rewritten as 1.29. Now we have to determine how many decimal places do we move over with this thing. So if we're looking at this, we move over 1 place, 2 places. Okay, so we have an n value of 2. And now we need to ask ourselves, is this thing going to be 1.29 times 10 to the second power or 10 to the negative second power? And again, we do this by going back to the original number that we've been given. What is this original number? It's 0.0129. This is a number between 0 and 1, meaning we're working with some form of a very small number, which means that for our final answer, we are going to have 10 to the negative second power. So our final answer for this is going to be 1.29 times 10 to the negative second power for this problem. And there we go. We just converted both of these numbers from decimal notation into scientific notation. From here, let's take a look at converting scientific notation into decimal notation. Now, this is a process that does not take a whole lot of time to do. We just really need to determine which direction are we moving the decimal place. So our process is for this is we're going to determine what is the exponent n we've been given. We need to move that decimal point then, wherever it starts off in the original scientific notation, n many places. If we have any zeros or any blank spots that show up, we're going to fill that in with placeholder zeros in here. Now, the direction that we move the decimal point, to the left or the right, purely and entirely depends on if the exponent is a positive or a negative number. If it's a positive, the decimal is going to move to the right. If it's a negative, the decimal is going to move to the left. We'll take a look at these two examples here to see how that plays out. So looking at our first example, we're going to convert 9.25 times 10 to the fourth power into decimal notation. Now remember, decimal notation is just kind of our standard way of writing these things out. So, following our process, we need to determine the exponent n, the factor of 10. Okay, so we've got 10 to the fourth power. So that means this decimal is going to move 4 places. So which direction is it going to move? Well, looking at our process, it tells us move the decimal n places, adding zeros if necessary. If the exponent is positive, move the decimal point to the right. So my recommendation for doing this, let's write out the number that we were given. And we're moving 4 places to the right, so let's write that out. So we're going 1, 2, 3, 4. New decimal place there. Any blank spots that we have in here, we're going to fill in with zeros. And then for me personally, I like having an extra 0 at the very end just after the decimal place so I can make sure it's really clear. Here's where the decimal point starts. So my new number is listed here, 92,500. And there we go. We've just converted this thing into decimal notation for our final answer. Let's take a look at the second example, which tells us we have 7.5 times 10 to the negative second power. Yet again, we're going to be determining what is our n value. 10 is being raised to what power? Okay, negative 2. Okay, so the negative tells us the direction. The number tells us how many places. So I'm moving 2 places in the left or right, positive or negative direction. Let's see. Well, based on our process, it says in 2b, if the exponent is negative, move the decimal point to the left. So we're moving the decimal point 2 places to the left. So it means we're going to come over 1, 2. Now we're filling in with placeholder zeros. Again, I like to have a decimal point in front and at the very end personally. So when this thing is rewritten, I have 0.075 as my final answer. And that is our process for converting back and forth between scientific notation into decimal notation. The last thing we're going to be looking at with scientific notation is multiplying or dividing numbers that are written in scientific notation. So a process that we have for that and some general properties are listed right here. Again, I would recommend that you write down the highlighted bullet points and the highlighted parts here. I would take a moment to pause this if you need to. Go ahead and write this down before we go into and talk about this a bit further. But the main thing that we are going to be doing is we are going to be multiplying or dividing these scientific numbers together in very specific parts. If we see here, we're going to do the operation with the leading A values. That could be a 1 point something, it could be a 5 point something, 2 point something, whatever it may be. And then we're going to actually do the operation where we're multiplying the 10 to the nth power together. Now we're going to be writing our final answer into scientific notation here. So our general way of writing this out, this assumes that we have everything written in scientific notation at the very beginning of the problem. So it says, okay, I have A times 10 to the m times B times 10 to the n power. So I'm going to multiply the leading parts together, and I'm going to multiply the tens together. And if the bases are the same for the tens, what do the exponents do? They add together. It's just our previously learned exponent properties coming back into play here. Same thing with division. I'm going to divide the two numerical parts together here. And then when it comes to the 10 to the raised powers, I'm doing the m minus n power here. We see that written out in our final answer here. So as we're going through, again, take it in parts. Take the real number part, take the 10 to the whatever power part, and deal with those and work with those two things separately from one another. We'll take a look at these two examples that we have down here, see how this plays out. Looking at our first example, we have the scientific number 8 times 10 to the 4th power divided by 2 times 10 to the negative 1st power. So as we had with our process and our notes that we wrote down, we have two scientific numbers that are dividing together here. So my recommendation is let's split this thing apart and do it in parts. I'm going to divide the numbers in front together. I'm going to write that out for myself, 8 over 2. And then I'm going to work with the powers of 10 dividing together. Now again, that's going to utilize the quotient rule, so this thing is going to be written out as 10 to the 4 minus negative 1 power. So we have this initial setup for ourselves. Great. Let's actually compute this thing now. So 8 over 2, it's going to give me 4. 10 to the, well, I have 4 minus negative 1. I really don't like double signs showing up in there, so I'm just going to rewrite this to 4 plus 1. Much clearer now. I'm going to get 4 times 10 to the 5th power as my final answer. So again, we're just going to do these things in small individual parts. If you're working with these and you have larger, grosser numbers showing up in front here, that 8 is maybe 8.2735, that 2 is 2.9105 or 3 or something like that. When you're actually going through and dividing them together in this step here, you're more than welcome to use a calculator to number crunch those and figure out what those become. I think it's much easier to do, and I would highly recommend we do that. So let's take a look at our second example we have here. We have 12 times 10 to the 2nd power over 4 times 10 to the negative 2nd power. All right, so we've been given this thing. Let's work with each of the values that we've been given. So we're going to work first with numbers in front, And we're going to work with the powers of 10. Again, I think it's very, very helpful to write this thing out for yourself as these separate parts. See how we get to an answer there. Okay, well, 12 over 4, that's just going to become 3. And then 10 to the second minus 2. Again, I don't like double signs in there. They always mess with me, so I'm going to adjust that. 10 to the 2 plus 2, much better now. And I'm going to be getting 3 times 10 to the 4th power. There we go. We have our answer there. The last thing we need to do is make sure that our final answer in both of these situations, and any of these situations when we're multiplying or dividing scientific numbers, is actually written in standard form. So we need standard form, I should say, scientific notation. So we need to make sure that this leading value is indeed greater than or equal to 1, but less than 10. We need to make sure that the leading number there is greater than or equal to 1 and less than 10. If it isn't, then we're going to go back to our previously learned methods and start with the decimal point, move it over accordingly. Or maybe it's going to be going in the opposite direction. It all depends on what we get coming out of these operations here. But as necessary, we need to go back and adjust and rewrite our final answer into scientific notation based on the final answer numbers that have been given to us. If it's an instance like these two that we have right here, where there's no additional work that's necessary, great, we're done, and we can leave our answers there. But otherwise, just keep a lookout for that on a couple of these problems. I'm not planning on giving you guys anything particularly wild and crazy with that, but you could see that in future classes or other types of classes. Primarily physics or chemistry has a lot of that showing up. But for the purposes of what we're going through and doing here, we're not going to do anything too particularly wild and crazy in that regard.